Hey guys, sorry I'm a bit late today. It's almost 10 o'clock now, and I'm trying to record for the third time. Like always, whenever I start a new chapter, it I have to learn a lot. I mean, I have to go through a lot in theory, and usually that takes a bit more time, I guess, than just solving questions. Should be the opposite way around, but yeah, for me, theory is harder. Although I have seen this theory before and I've worked with it in my data DSA class, it's still kind of difficult. Probably I should have paid more attention. But anyways, today, like I said, I looked at linked list. So what is a linked list? Let's dive right into it. So usually there are an array with number of elements. Linked list is a special data structure where each element is stored in contiguous location like this, and they are linked using pointers. Now, pointer is a really common concept in languages like C or C++. Um, yeah, it's kind of essential to learn it. But in Python, the linked list is there's no star asterisk like in C++. So instead, we define it as an object and class. But for now, let's continue explaining what a linked list is. So basically, these are called nodes, and they are pointers, the arrows, and they're linked, right? So that's why they're called linked list. And this, you can understand it as each node having two parts. So first part is data, and the next part is the next. So the next pointer, this pointer stores the memory address of um, the node in the next sequence, while the data, it holds the actual data. So like in an array, um, 1, 2, 3, like so on and so forth. Only difference is that in array, each element already holds a memory value and the data. So, and here it's linked. So the next, this part points at the next node. Yeah, so this is the basics of linked list. And how is it advantageous over uh, the array, the use of array? It is because array stores elements contiguously in memory. So you can have 0, 1 random access. What it means is that, let's say there are millions of elements, like 150,000. Yeah. To access like 100,000th element in an array, you just can access it using an index. But so that will be O1 time complexity. But in a linked list, that's not possible because you have to start from the head, which is the start of the linked list. You have to go through, iterate through all the elements, all the nodes, I mean. So that would be ON. So in this case, um, we have to find 100,000, we have to access 100,000 node. So that would be O 100,000. So in that case, it's pretty disadvantageous. But um, compared to array, how it's advantageous is that it allows really efficient sizing and efficient insertion, deletion. So if you want to delete a node, that's O1. if you want to just insert an element or node, that's also O1. So in that sense, it's more efficient than an array. There are two types of linked lists. One is a singly linked list and another one is a doubly linked list. But let me first show you a code where I can describe how the simple linked list works. I hope my video is showing. I need to go get a haircut tomorrow. Okay, so so I said in Python, right? Class list node. We define init, simple object-oriented programming, self self.val equals val and self.next is none. Here val is the data and next is the next, the two parts of the node, right? Now let's say one is list node 1, 2 is list node 2, 3 is list node 3, and 1 dot next. So we're pointing to the next node, right? So that should be 2. Here we're connecting the linked list, so to make a linked list, 2 next is 3, and where do we start from? Yes, 1. So head equals 1. Yes. So if we print, for example, head val, it will be yeah, it will be the 1, right? Because that's the start of the linked list. If we print head dot next dot val, then that will print the next node of the linked list. So that would, in this case, would be 2. And then if we do next dot val, that would be 3. So that's a simple use case of a linked list. This is efficient because why? Insertion and deletion can happen in O1 time complexity. Yes. In C and C++, that would be a bit different because you can simply use asterisk, PTR asterisk. But yeah, Python is much more easy to understand in terms of visualization, I believe. So yeah. Now. What was I talking about? Yeah, there are special techniques. I think one was Sentinel nodes, where you put the dummy nodes in the beginning and end of the list to simplify edge cases and insertion and deletion to even further simplify the cases. There are dummy pointers. So temporary pointers are used during traversal when you're traversing through all the nodes to avoid losing the reference to the head node, because that could happen quite commonly when you're iterating through thousands and millions of nodes. Also, you can chain dot next call to navigate through the list. I kind of showed you how it works here, as you can see, but yeah, we're gonna go through it later or tomorrow through example. So let's talk about simple operations. On linked lists. So like lists, no, like okay, so like for example, lists. If you want to insert an element, that's only possible in the front part or the last part, right? Using append. In insertion in array, I mean in linked list, that's possible at the beginning, at the end, and also after a given node. So you insert when you want to insert it at the beginning, insertion at beginning. You insert a new node and update the head reference. If you want to store it at the end, you traverse to the last node, and then update its next reference by adding a new node. And if you want to insert it at a given node inside a multiple layers of linked lists, then you update the next reference of the given node and the new node. So it's all about the next reference, right? Also in the at the end, especially for the end and given node, if you want to insert it. Traversing is also simple. Traversing is just iterating over each node, starting from the head. Deletion, you can do it using a key or by position. So when you're trying to do it by key, you traverse the linked list to find the node that you want to delete and update the previous node. Previous nodes, next reference. So when you were inserting, so let's say that there are multiple nodes. When you were inserting, you want to update the next reference of the given node if you want to put it after a given node. So you update this reference if you want to change here. But if you want to delete this node, you now traverse from the beginning, from the head, to find the node and update the data of the previous node. No, I mean, not the data, but the reference of the previous node's next reference. So this part, right? So this part was the data, and this part was the reference. The next. This part was the data, this part was the reference. Sorry, I should have put this one next. That has to be updated if you want to update the given node when you were inserting. Not only by key, but you can also delete by position. So how you do it is you can traverse to the given position and update the previous node's next reference. So that's pretty much the same as the key, right? You just traverse to find the node in the key, and in the position, you just traverse to the given position. So that's pretty much the same. When you're searching, you traverse the list to find the node with the specific value that you want to search for. Also, when you're reversing, you reverse the direction of the next reference in the list. So what you're changing most of the times is the next reference, not the data itself. Well, that makes sense because you're not going to change the data unless you remove it or delete it. So it's all about the next reference, the right part. I'm just putting it as the right part, just so that it's easier to visualize it. Data is here, next reference is here. Yeah. So that was it for today. Quite a short one, just going through the theory. From tomorrow onwards, we're gonna, really go into examples and see how it can be implemented using classes and objects, pretty much because we're using Python. But yeah, thanks for listening, and thanks for learning with me today as well.